Hi, we are Team 11. The members of our group are Maximus, a mechanical engineer, Mario, a mechanical engineer, Marcus, a mechanical engineer, and David, an electrical engineer. Our advisor is Professor Bird, and co-advisor is Professor Werner. Our senior design project is the design of a dynamic balancer that will be used to demonstrate a dynamics lab for future SUNY New Paltz students. Students will be capable of observing an imbalanced rotating system and challenged to determine techniques to balance the system. The figure shows a CAD model of our dynamic balancer design. The main components are the motor, correctional plane, tachometer, accelerometers, bearings, shaft, belt pulley system, main base, movable weights, and the motor mount.
Static balancing is when the center of mass is located on the axis of rotation. Demonstrated in this video, the system is unbalanced. The center of mass is shifted towards the weight on the disc. When the mass is lifted up to the left or right of the axis of rotation, it rotates back down.
Using the sum of forces equations shown, we are able to create a visual aid on MATLAB that takes in the size and location of the unbalanced weight from the user and will output the angle at which the counterweight will need to be placed, as well as the two different masses for the two radii we have available on our discs. This can be done for however many weights start on the disc.
In this demonstration, the apparatus is statically balanced. It can be observed that the disc will maintain its orientation at any position due to the center of mass being at the axis of rotation. This is due to the equal masses shifted by 180 degrees equidistant from the center of rotation.
For a system to be dynamically balanced, there must be no out-of-balance centrifugal forces trying to deflect the shaft and no out-of-balance moments trying to twist the shaft. As seen in this demonstration, the masses are opposite each other on different planes, causing both twisting and deflection of the shaft. When the motor is spinning at 1300 RPM, the vibrations due to these unbalanced forces can be seen. The system vibrates and moves across the desk while the accelerometers attached under each bearing pick up and record these vibrations to later be used for balancing.
The blue and yellow lines represent the accelerometer outputs in volts as read by the NIDAC. As speed increases, the peak-to-peak values of these voltages also increase. This is due to more vibrations of the shaft and the system as a whole. As we reach our peak speed of 1300 RPM, we see the highest voltage values. This is when our entire apparatus was moving as previously shown. Using the sum of moment equations, students will be able to calculate the location of the counterweights needed and will be able to observe the effect this has on the vibrations of the system.
In this demonstration, it can be seen that the system is dynamically balanced. This is due to a minimal vibration on the bearings, resulting in no stress and displacement components in the vertical direction at each accelerometer. This balance is due to the centrifugal couple of one disc canceling out the centrifugal couple of the other disc.
Unfortunately, the accelerometer readings do not show the results as clearly as the demonstration. This will be a major focus of the team for next semester. The readings were nearly identical to the unbalanced system, and we have already discussed some possible causes as well as ways to fix this.
For our design going forward into next semester, we will try to improve the readings given by the accelerometer so that it obtains meaningful data as well as reducing the noise being recorded. We want to increase the mass of the weights because the ones shown in the previous demonstrations are only 10% 3D printed parts, so they don't have much mass to them. We will increase the distance of the planes. Heavier weights and larger planar distance will amplify the readings from the accelerometers. We will develop a more accurate belt design. We will design a motor mount that allows the user of the dynamic balancer to easily attach and detach the belt. We will develop a code that enables the data from the NIDAC to output in MATLAB. We will also increase the safety so that the lab can be conducted many times with no issues.